Hello. I'll talk about Lemma 3, which is about Lemma 3 of Theorem 16.16, Lagrange's four-square theorem. And here's the lemma as following. So, if there exists integers a, b, c, d such that 2n can be represented as a sum of four squares, then there also exists integers a, b, c, d such that n can be represented as a sum of four squares. So basically it's saying that if 2n can be represented as a sum of four squares, n can also be represented as a sum of four squares. Lemma 3-2 just says that if 3n is expressible as a sum of three squares, then n is also representable as a sum of four squares. Right? Yeah, four squares. Yeah. So let me go over the proof now. Okay, so for the first one, we have that 2n is equal to a squared plus b squared plus c squared plus d squared. Well, this implies that since 2n is even, we need to know we know that there will be even number of evens. So in the set A, B, C, D, there will be the even number of ands, odd, even number of odds. So we can pair these things together, so such that x is congruent to y modulo 2 and z is congruent to y modulo z is congruent to w mod in mod 2. So we're going to rearrange this set A, B, C, D such that it is equal to x, y, z, w, but x is congruent to y in modulo 2 and z is congruent to w in modulo 2. Then what can we do? We can rewrite 2n as x squared plus y squared plus z squared plus w squared, which can be written as this sum. You can just expand this out and check. And since x is congruent to y and z is congruent to y, z is congruent to w in modulo 2, that means that all of these are integers, which completes our proof. So we just divide by 2 and plug in the 2 into this parentheses. So that lemma was easily proven. Now let's move on to the second lemma. So if 3n is can be written as a squared plus b squared plus c squared plus d squared, then first of all, since a squared since 3n is divisible by 3, we're going to check modulo 3, okay? So suppose none of a, b, c, d is divisible by 3, then these would all be congruent to 1 plus 1 plus 1 plus 1, congruent to 1 modulo 3. So that will yield a contradiction. So there has to exist one of a, b, c, d that is divisible by 3. And we're going to log say that's d, okay? So in the case 1, what if 3 does not divide a, b, and c? Then if we think about it, a squared is also equal to minus a squared. So we can kind of change ABCD such that a to like minus a, or b to minus b, or like c to minus c, such that we can make these kind of substitutions so that a is congruent to b, and we can assume that a is congruent to b, which is also congruent to c in modulo 3. So now if we write 9n as 3a squared plus 3b squared plus 3c squared plus 3d squared, we can write this as a sum of four squares as the following. You could expand this and check. And the motive for this actually comes from this identity, which basically says that sum of four squares which is kind of an extension into quaternions, but I'll explain that later. So this identity provided the motive to come up with this identity. And if we divide by 9 on both sides, we get this sum, and it's equal to this this thing, which I won't like tell, well, which I won't actually say it out because it might waste time. So since we know that A is congruent to B is congruent to C, and 3 divides D, this implies that A plus B plus C is divisible by 3, and also that A minus B divides 3, and 3 divides D, so A minus B plus D is divisible by 3, and 3 divides B minus C plus D, and 3 divides C minus A plus D. Therefore, these are all integers, so they satisfy the condition. Okay, in the case when 3 is divisible, 3 divides A, B, and C, then it is more obvious because they're all divisible by 3. So all of these will be integers, which proves our claim.